Welcome. Let us revisit the homogeneous evolution problem, what we have done in the last lecture, very quickly. So this is the homogeneous evolution problem. Why do you call it evolution problem? Because in this Cauchy problem, the operator, it is non-autonomous operator, so it depends on time explicitly. So here this d phi dt is equal to at phi t is the equation, and with initial condition phi is x, where t is between s small s to say some capital T. Okay, so we are here presenting only the finite horizon case. Okay, and then what we have done, we have introduced the solution operator. So homogeneous evolution problem is this one. For this, the solution operator is written as capital U of t comma s x. Okay, what is this? How is it defined? It is defined as a solution of this equation. See, this equation gives me one solution which depends on time. So it is, time varying. So this is like a path on the Banach space, capital X, correct? So at time s, it takes the position small x, and then it varies. Okay. So this is phi of t, and this solution operator capital U is a two-parameter family operator, is defined this way that when you apply this operator at the initial position small x, okay, and then what you are going to get is a solution at time t. So given if at s, if the position was x small x, at time t you are going to get the solution at time t. Okay, so this is the definition of the solution operator. Then we have seen the theorem. This is a very special case where this operator is a bound linear operator, like matrices, correct? So it's a bound linear operator. So then then one can expect a very nice result, because for the initial value problem, that means time autonomous case, there one could get actually that for each and every initial point small x in the Banach space, one can get the solution, and the solution was also written in a very simple manner. Just it was ttx, where tt is the semigroup generated by the operator. So here also we are going to get similar kind of things if we assume certain things. So here t to at, if this map is continuous map, for autonomous case, it is just constant map. Constant map is continuous anyway. So, but here when we allow a to vary with t, this at is continuous. And then for all small x in capital X, this homogeneous evolution problem has a unique classical solution. Okay. Next, we introduced what is evolution system. Evolution system, or in short ES, this is a two-parameter family of bound linear operators. So UTS, we write down this way, and this this kind of two-parameter family of operators would be called ES, or evolution system, if following two conditions are true. That is, USS is equal to I identity operator. When there is initial and final times are same, then it's just identity. And URS is equal to UTS. So that this is like a generalization of the semigroup property. Okay, that we have discussed in quite detail. And another thing is that regularity property, that TS to UTS is strongly continuous. What does it mean? That means TS to UTX, the point in Banach space. So that map is continuous with respect to the variables T and S. Okay, so example, that if we have a C0 semigroup TT and we define UTS as capital T of T minus S, so then this forms the evolution system. So this is an example. Furthermore, if capital A is the infinitesimal generator of a C0 semigroup TT, okay, for each small x in the domain of A, we can write down, we can get the following things. The derivative of UTSX for this UT, okay, we are going to get A UTSX, and derivative with respect to s, if we do, then we are going to get minus a UTSX. Okay, this is trivially obtained because we know that derivative of TTX is equal to a TTX. So just we are applying because we are applying this relation here to obtain these expressions. Okay, next point is that evaluation system you associated with AT. Okay, so this is the thing we are going to see now today, that what do we mean by evaluation system associated with family of operators. See, there is no single operator, the family of operators. Okay, t greater or equals to 0. Okay, so first thing is that this you should be an evaluation system. Okay, a 2-parameter family which satisfies these conditions. So it should be evaluation system. And then for each small v in the domain of AS, remember here A is not a single one, there are plenty of A's. So one should be very careful that which A we are talking about. So here time S is the initial time, so we put S here. So if V is in the domain of AS and then UTS V, okay, that should also belongs to domain of A of T. Okay, so if V belongs to in the domain of AS, then UTSV, which is also a member in the Banach space, okay, so that is actually solution, that is phi T. Okay, so that should, I mean, we don't require that to belong to the domain of the same operator, but domain of the operator A of T. So this condition actually put some condition on the family of operators AT also, correct? Because for any arbitrary family of operators AT, you may not be able to get anything, any such existence. Okay. So anyway, so we are going to talk about the sufficient conditions, the AT, for which one can assure existence of such evaluation system. That is a separate topic. We are going to see today also that thing. But here we are talking about when these things are true, then we say that this capital U is associated with the family of the operators AT. Okay. So the third point is that for S and R, okay, S less or equals to R, so here we require that the expression of the derivative, the how A and U are related. Okay, so this is the derivative, the ddt of UTSV is equal to AT UTSV. So it looks like almost like what is written above, but of course there is some difference because here A was constant, it was not a function of time, but here it depends on time. So ddt of UTSV is equal to AT USV is one condition. Another thing is that derivative with respect to S variable, then we know that capital T minus S minus sign comes here. So I should expect a minus negative sign here. So negative sign UTSASV. So it is important to notice this difference that here A comes first and then U, here U comes first and then A. Okay, and here also one must be very careful that the condition that here the second property was crucially used, that when V is in domain of AS, then UTSV is in domain of AT. Otherwise this expression makes no sense, because if V is in the domain of AS, which was assumed here, then UTS, if that is not in the domain of A, then this doesn't make sense. Okay. Anyway, so and here there is no such trouble because V was anyway in the domain of A, so it makes sense. Okay, A is V. Okay, and U is anyway defined on the whole Banach space. Okay, so this is the definition of evaluation system associated with a family of operators AT. Okay. So, I mean, why are there two different definitions? I mean, so this is just definition of evaluation system. When can we call a family of boundary linear operators an evaluation system? We can call when this is true. But this is a different question. Here we are asking that given a family of operators AT, when can we say that a particular evolution system is associated with that family of operators? Okay, go to the next slide. Here, this slide we have seen in the last lecture, the inhomogeneous evolution problem, IEP in short. So this there is a typo here. I should have written here phi. Okay, d phi dt is equal to AT phi t ft, phi t plus ft, and then phi s is equal to x. So this is true for all t s to capital T. Okay, so this is the equation, and here we call this inhomogeneous because of the presence of small f. And here f is assumed to be L1 as before, because when we have discussed the inhomogeneous initial value problem IIVP, there also we have assumed f to be in L1. Okay, so we cannot drop any assumption there because it is more generalization. In certain cases we have to put more condition but not less for existence of mild solution or classical solution, whatever we discuss. Okay, where f is in L1, and assume that there exists an evolution system associated with AT. Okay, so then the function phi, okay, which is a continuous function from the time domain to the Banach space x, given by phi t is equal to UT x integration 0 to t UT r f r dr. So this is called the mild or generalized solution. So it is very easy to recognize that this is nothing but the extension formula for variation of constants. Okay, so this thing also we have discussed in the last lecture. Okay, next we study when can we associate an evolution system with a given AT. That is the main important thing, right? So this is like, a statement similar to the Hill-Yoshida theorem. So when given a IEP or HEP, or in other words, given an evolution problem, we would be given a family of operators AT, and then to write down its mild solution, we first need to know whether we can find an evolution system associated with this family of operators. If we can, then we are going to see that we can write down. So here, say for example, this is if there, assume that there exists evolution system, then you can write down the mild solution using the evolution system. Okay. So for this question, whatever answer we are going to get, that would give us a sufficient condition, right? Set of sufficient conditions under which a given family of operators would admit an existence of an evolution system associated with this. Okay, and we would assume those sufficient conditions throughout for our development. Okay, so here some more new definitions are recalled here. So here, let X be a Banach space. A family AT of infinitesimal generator of C0 semigroup on X is called stable if there are constants capital M, which is not less than 1, and omega, which is non-negative, so greater or equal to 0, such that the resolvent set of AT includes this open interval omega to infinity. Okay, this includes this for each and every t between 0 to capital T. Okay, so this is saying that, okay, omega is some omega, so that means at least there exists, this row for each and every t, AT would have the resolvent set, but the intersection of all these includes at least one ray. Okay, ray will mean that, okay, omega to infinity, this set. Okay, this is one condition. And another condition is that for every finite sequence, T1, T2, Tk, k is some natural number, where this T1, T2, Tk is less than or equal to capital T. So between 0 to capital T, we are considering a partition basically, okay, some finite sequence, increasing sequence, and then for this T1, T2, Tk, we construct this product. So this should be understood or read in the following manner. R lambda AT1, then composition R lambda AT2. Actually, the smaller numbers come on the right. Okay, so in a particular order, in the order of this time, because these operators need not commute each other, so this product should be understood in a particular order. So after fixing this order, then take the norm, and then that is less than or equal to capital M divided by lambda minus omega to the power k, and this is true for all lambda greater than omega. So surely this is an additional condition on the family AT, correct? Because this should be true, satisfied, for every lambda greater than omega. Omega would be a fixed number which does not depend on t. And then, so here k1, k is any arbitrary natural number. So this thing should be true. So this puts a condition, okay, and if a family satisfies these two conditions, we call that family a stable family, okay, a stable family. The constant omega appearing above is called also the stability constant, okay. Okay, so in Hill-Ridge theorem also we have seen similar kind of, upper bound there on the reservoir operator. So example, a family AT, okay, so this of infinitesimal generators of contraction semigroups is stable. Why? Because for contraction semigroup, this capital M becomes 1. And then the omega also becomes 0, because they're all these ATs, etc., those are norms are always less than or equals to 1. Okay, so there one gets that this would be a stable family of semigroups. Now another new notion, what we call as part of it is some sort of restriction of an operator in a subspace, but it's not strictly speaking a restriction, but even more one has to be careful that restriction not only in the domain but also we require a desired property on the range space also. So we define this manner. So let TT be a C0 semigroup with A as its infinitesimal generator. A subspace Y of X is called A admissible, okay, A admissible if it is an invariant subspace of TT. Okay, so that means that from any point y, if we take a point from y, small y say, and TT of y would also be in y. Okay, so this is an invariant subspace. Second is that TT restricted on y, okay, is a C0 semigroup in y. Okay. So that is that means that from y it takes value to y itself. Okay, C0 semigroup on y. So definition of part A of A in y. So what is this? This is if capital A is a map, it is boundary, is a linear map, okay, on X, but not on full X, but on some domain of A, which is a subspace of X. So A from dA to X, and Y is a subspace of capital X. Then the part of A in Y, okay, it is sounds quite similar to the restriction, because A was defined on some domain of A and Y is another subspace of X. Okay, Y need not be strictly subset of the domain of A, but Y is some other linear subspace. So part of A in Y is the linear operator A tilde given by A tilde X is equal to AX. What is A tilde? Where is it defined? It is defined for all point X which is in the domain of A and intersection of Y. Okay, so the point X which is common in the subspace Y and the domain of A. Okay, and such that the image of Ax under A is also in Y. Okay, so we choose X from Y also in domain of A, and then we look at the image if Ax also in Y. So those points, so this would surely be a subset of domain of A and Y. But the good point is that it tilde takes point X from here to Y itself. Okay, so it is going to Y itself. Okay, so this is given by A tilde X is equal to Ax. Okay, so it is like, you know, exactly the A map, but the domain should be carefully chosen. Okay, that we call as a part of A in Y. So example, if Y is an invariant subspace of capital A, okay, then A restricted to Y is precisely A tilde. Otherwise, it is not true. Okay. Okay. Next, we assume that Y denotes a densely and continuously embedded subspace in X. Okay. So here in this above discussion point 12, we were discussing some Y is some subspace, but here now onward we are going to put a particular condition on Y. We are going to put that, okay, this Y denotes a densely and continuously embedded subspace. What is the meaning of densely defined? That means the space Y under this norm, okay, whatever the topology, if we take the closure of that, that is X. And then what is the meaning of continuously embedded? That means the identity map from Y to X. Y is subspace of X. I can take identity map from Y to X in the sense that the domain we take the topology, the norm of Y, and the right hand side, you know, the codomain we take the topology coming from the norm on X, and then with these two topologies, okay, so the identity map becomes continuous. Okay, so using these two, if these two are true, then we say the densely and continuously embedded subspace of Y, and we are going to assume that, okay, throughout we are going to assume that. So before going to the next slide, we look at this remark: if Y is admissible, the part of A in Y is the inferenceable generator of a C0 semigroup itself. Okay, and this coincides with the restriction of the semigroup generated by A to the subspace Y. Okay, so what does it mean? It is like in diagram commutes kind of things. It is saying that so if I have the operator A here on the domain of A in the Banach space X, and then from that that A, assume that generates a C0 semigroup TT. Okay, and from this A again with the given Y, we can get a part of A, and then the part of A is an operator. From that also I can get another semigroup generated by this operator. Okay, so assume that all this we can do. Then here I have a semigroup TT, here I have a T tilde say. Okay, and then this is saying that the restriction of TT on Y is precisely T tilde. Okay, so that is the remark. Next, we talk about existence of evolution system in hyperbolic case, assumptions and notions. We start notations. So there are three conditions we are going to stick to. So that is called hyperbolic case. The name actually arises from the application of this theory in different branches of partial differential equations. So here there are three conditions. I'm reading first one first. A of T is a stable family. Okay, so the stable family I have just discussed here. So this is a stable family. A family of operators is stable if these two conditions are true. Okay, so and then the omega is stability constant. Okay, here first is that AT is a stable family. Okay, so that is one condition. H2 is that Y, okay, is AT admissible for all T, okay. So we assume that Y is this, and A tilde T, okay, which is a part of A in Y, that is a stable family. So H1 says AT is a stable family, A2 says that even its parts in Y, that is also stable in Y, and Y is AT admissible. Third condition is that for every non-negative zero capital T time, okay, Y is included in the domain of AT for whatever time you have, the whole horizon here. So and then AT, okay, from Y to X, I can now talk about AT from Y to X, because domain of AT includes capital Y. So for every member in capital Y, AT of that member is well defined. So AT from Y to X is bound linear, and the time to T to AT is a continuous map. Okay, so this is important because if AT is not bounded linear, then I cannot talk about continuity in this sense. Okay, so it is bound linear operator, and then this is continuous in the norm topology. Okay, so under the norms topology. Okay, so this is H1 is to H3. So if any family of generators, family of operators AT satisfies these three conditions altogether, then we call that that family is satisfying the hyperbolic case. So then theorem. So let AT satisfy H1 to H3, H1, H2, H3 with stability constant M omega M tilde omega tilde. Why do we write down 4 instead of 2? Because these capital M and omega are stability constants coming from the operator A, okay, and M tilde omega tilde is coming from its part in Y, correct? So A tilde, okay, coming from A tilde. Then there exists a so under this condition there exists a unique evolution system, capital U, in X. Okay, unique evolution system. So this H1, H2, H3 with these three conditions, there is a unique evolution system, and satisfying some user properties, that norm of UTS is less than or equals to capital M times e to the omega T minus S. Okay, so these are direct extension what is true even for the semigroup of operators TT. And another thing is the derivative here. Since there are two variables, so one should be very careful with respect to which variable one is differentiating. So d plus dt, okay, so the derivative with respect to time t, but positive derivative, and then put t is equal to sk, so positive slope, okay, positive slide slope, okay, so that is equal to ASV. Okay, why should it not depend on time t? Because here time t is equal to s is substituted. T is equal to s has been substituted, so this is ASV. Third property is that partial derivative with respect to s variable. Okay, so as I have said here earlier, that for the special case where A is time autonomous, this is like capital T of T minus S, and then due to the minus sign one should expect a negative sign here also, is equal to minus U of capital A of V. Okay, so this is a theorem which talks about existence of evolution system. Okay, and without any doubt, it clarifies that this H1, H2, H3 are form a set of sufficient conditions. Okay, next we come to another definition. So this is called y-valued solution. So here first thing is that given inhomogeneous evolution problem, we have already seen that what should be the expression of mild solution. Okay, and then we asked the question that while writing the mild solution, I really do require an evolution system, and then under what condition or the family of operators one can assure existence of some evolution system. And for that last theorem answers to that question, that if the evolution system satisfies H1, H2, H3, then there exists one evolution system. So to solve one inhomogeneous evolution problem, one just needs to check this H1, H2, H3. If one is lucky and those conditions are true, then one can get evolution system from the earlier theorem, and then one can apply that theorem, okay, for writing down the mild solution of IEP, okay, using the extension of formula for constant of formula for variation of constants. Okay, but by this we are settling down the question of existence or uniqueness of mild solution, how to write down that. But the question about classical solution has yet not been discussed. The thing is that for classical solution one needs much more stronger condition. It is difficult to find out a particular sufficient and necessary and sufficient condition for on the family of operators AT, so that the equation would have a unique classical solution. Okay, so here this remark says something here, that unfortunately we do not know any simple conditions that guarantee the existence of a classical solution to IEP, okay, inhomogeneous evolution problem. In the hyperbolic case, even if small f is equal to 0. Okay, so hyperbolic case means H1, H2, H3. Okay, so those appear a little strong, however those are not that strong. So for example, H is bound linear operator, so this is very strong, you know, but one should also look at that if it is x to x, then just really strong. But here I have y, okay, so y may have some different norm also, okay, as long as y remains continuously and densely embedded in capital X. So AT is bound linear operator here with these norms choice. So now you go to the next definition, that what is y-valued solution. So what are you doing here? Since answer to the question of classical solution is difficult, we are looking at some another class of solutions which is also classical solution, but that requires a little more condition that the solution is in y. Okay, so let us see the detailed definition here. Y-valued solution: a function u as a function of time, okay, so continuous function from s to capital T to v, and then also once continuously differentiable on st to s to capital T x, okay. So a function u which satisfies the inhomogeneous evolution problem is called y-valued solution of IEP, okay. So main thing is that here this function should be solution of IEP, okay, and second thing is that it should be continuous function of in y, and it should be differentiable also. But for differentiability we don't take the norm coming from y, but norm of x, okay. Theorem: so h1 to h3 are true, so that is our assumption. if h1 to h2 h3 is this hyperbolic case, and small f is continuous function, okay, a continuous function on these S2 cavity. So when you say that it is some function is a continuous function on a compact set, here it is small S2 cavity. So that means it is automatically bounded, and a bounded function with respect to the Lebesgue measure is integrable. So L1 property we don't need to say separately, just f is continuous clarifies that on the compact set. So if h1, h3 are true and f is a continuous function, and the inhomogeneous inhomogeneous evolution problem has y-valued solution. So here we are assuming if it has y-valued solution, then the conclusion is that the solution is unique and that can be written as the mild solution. So, and identical to the mild solution. What is the mild solution we are talking about? We are talking about this relation. Phi t is equal to utsx plus integration small s to t utr for dr. Okay, so this is the mild solution, generalized solution to the IEP. So here we mean that under that condition, h1, h2, h3, and f is continuous, and one would get that the solution is identical to the mild solution, okay, the one which is an extension of the formula for variation of constants. So that is one theorem. The another theorem says that, so in this theorem we have assumed existence of y-valued solution, but here we are going to give sufficient condition for that also. So let AT satisfy h1 to h3. So since it satisfies, this family of operators satisfy h1, h2, h3, so that assures existence of u, the evolution system. So that means that we can write down the mild solution, and then if in addition to that you also satisfy the following two conditions, that UTS of y is a subset of y. Okay, so basically saying that y is invariant subspace under U. Okay, so so image of y under UTS is in y itself for all time, for all s and t. B is that for all small v in y, okay, so point in y, or is a much small subset, correct? So ts to utsv is continuous in y. So this is continuous, of course, in x, because this is coming from the evolution system, but we are asking that it is continuous in y, okay, so that is an additional condition. So if these two conditions are true for this evolution system U, and another additional condition on f, that f is continuous function, okay, so with these three conditions, then for each small x in capital Y, the IEP, inhomogeneous evolution problem, has a unique y-valued solution. So that means this is a sufficient condition, correct? Sufficient condition. So this suffices that of the existence of unique y-valued solution, which is identical to the mild solution. Okay, so let me stop here. Thank you.